So let's talk about matrix multiplication. I know, sounds a little dry, but stick with me. This is one of the absolute cornerstones of modern computing. We're talking graphics, physics engines, pretty much all of AI. It's everywhere. And for the longest time, everyone in the field thought we had hit a wall, that we knew the fastest possible way to do it.
Yeah, the entire scientific community was basically convinced there was this hard limit, a computational wall you just couldn't get past. Well, they were wrong. This is the story of the algorithm that came along and just completely shattered that assumption. So let's get into it.
All right, so before we can appreciate the breakthrough, we got to understand the problem, right? We need to look at the classic brute force way of doing things that had everyone so stuck.
Okay, so here's the standard formula you probably learned in school. It's pretty straightforward, but man, is it a grind. To get just one single number in your final matrix, you have to take a whole row from the first matrix, a whole column from the second, multiply each pair of numbers, and then add all those products up. And you have to do that for every single spot. It's a lot of work.
And that's where we get this infamous n-cubed running time. Why n-cubed? Well, think about it. You've got n-squared spots to fill in that final matrix, and to calculate each of those spots, you have to do n multiplications. So you've got n squared times n, which gives you n cubed. Simple as that.
Now, if you're multiplying tiny 2x2 matrices, who cares, right? N cubed is fine. But what happens when n gets big? I'm talking about the massive matrices used in weather forecasting or training a huge AI model. Suddenly, this becomes a gigantic bottleneck. The time it takes just explodes. It makes solving really big, important problems incredibly slow. This was the wall everyone thought was unbreakable.
So naturally, computer scientists started thinking, okay, how can we be clever about this? And they turned to a classic trick in the playbook: divide and conquer. The idea is simple. What if we just break this giant matrix problem into a bunch of smaller, more manageable matrix problems?
And the logic seems totally solid. You take your two big matrices, chop them up into 4 smaller submatrices each. Then, to get the final answer, you do 8 multiplications with these smaller chunks and just add the results together. It feels like we're onto something here, doesn't it?
And this formula you see here, that's just a fancy math way of saying exactly what we just described. The total time, t of n, is just the time it takes to do 8 of those smaller problems, plus the time it takes to do all the additions, which is about n squared.
But here's the kicker. When you actually do the math and solve this thing, you find out the running time is still n cubed. You go through all that cleverness, all that dividing and conquering, just to end up right back where you started, smack into the same wall. It was a total dead end. And that's where things stood, until 1969. A German mathematician, Volker Strassen, looked at this problem that everyone else had given up on and did something that seemed, well, kind of like magic. He found a shortcut that no one saw coming. Here's the absolute core of his insight. Everyone was stuck on those 8 recursive multiplications. Strassen figured out a way to get the exact same answer with only 7. It was just this brilliant, totally non-obvious bit of algebraic gymnastics. He basically traded one expensive multiplication for a whole bunch of extra additions and subtractions. And for a computer, that is a fantastic trade, because additions are way, way cheaper.
Okay, now look at these formulas. Don't panic, you do not need to memorize them. Seriously, the magic here isn't about memorizing the P, Q, and R. The key idea is that Strassen found these 7 clever combinations of the smaller matrices that, once you multiply them, hold all the information you need.
And then comes the payoff. Once you've calculated those 7 magic products, you can put the final matrix back together using only addition and subtraction. That's it. No more expensive multiplications. That is the whole trick, right there.
At this point, you might be thinking, okay, so what? We went from 8 multiplications to 7. Big deal. But it is a huge deal. Remember, this is a recursive algorithm. That means we're applying this trick over and over and over again on smaller and smaller pieces. That one tiny saving, it compounds. It's like compound interest for algorithms.
So remember that formula from before, t of n equals 8 times t of n over 2? Well, now it's t of n equals 8 times 7 times t of n over 2. Just changing that one single number from an 8 to a 7 has this incredible domino effect that completely changes the final result.
And when you solve this new version of the formula, you don't get n cubed anymore. You get, well, you get this funky thing, n to the power of log base 2 of 7. I know it looks weird, but what it means is that the whole scaling behavior of the algorithm has fundamentally changed.
So what is log base 2 of 7 in plain English? It's about 2.81. So the new running time is roughly n to the power of 2.81. And that was it. For the first time in history, someone had an algorithm that was proven to be faster than n cubed. The wall didn't just have a crack in it, it had been completely smashed.
And this chart really drives the point home. Look at that n cubed line. It just shoots for the sky. It's super steep. But look at Strassen's algorithm. It actually bends the curve. It grows much more slowly as n gets bigger. Now, it's not the holy grail of n squared. That's the absolute theoretical limit. But it was a massive, massive leap forward.
Okay, so this is all great in theory. Strassen's is asymptotically faster. That's a fancy way of saying it wins in the long run for huge matrices. But does that mean we should just throw out the old n-cubed method and use Strassen's for everything? Well, like most things in the real world, it's a bit more nuanced than that.
See, Strassen's algorithm has a bit more baggage. It has what we call a larger constant factor. All those extra additions and subtractions, plus the whole recursive setup, that takes time and memory. It's also not great for sparse matrices, matrices full of zeros. So what this means is that for smaller matrices, the good old-fashioned simple n-cubed method is actually faster.
And this leads to a really practical and clever solution called the crossover point. What modern software libraries do is they use a hybrid approach. They'll start with Strassen's algorithm for the big matrix, but as it recursively breaks the problem down, once the pieces get small enough to hit that crossover point, it switches back to the simple, faster, n-cubed method to finish the job. It's the best of both worlds.
But maybe the most incredible thing about all this is that Strassen's algorithm wasn't the final answer. It was the starting pistol for a whole new race. By proving the n-cubed wall wasn't real, it just opened the floodgates. It inspired generations of researchers to find even crazier, more complex ways to multiply matrices, pushing that exponent lower and lower. Today, the record is down to something like n to the power of 2.376.
And that leaves us right here today with one of the biggest unsolved questions in all of computer science. We know for a fact we can't possibly do better than n squared. I mean, you have to at least touch every element to write down the answer, right? But the best we've got is still a ways off. So the question remains, can we close that gap? Is there another, even more brilliant shortcut, another piece of magic just waiting out there to be discovered?